Previously, we saw about the intermediate prerequisites, in which we covered about the introduction to deep learning. We saw in detail about PyTorch functionalities, how to use PyTorch dataset and data loader, what is neural network, how to create it from scratch. And then we saw a detailed working explanation on forward and backward propagation. We created a simple ANN network. Followed by that, we saw about the types of each components which are involved in deep learning training, which includes activation function, loss function, optimizer. And then followed by this, we also saw about RNN networks in detail, which includes RNN, LSTM, GRU, by LSTM, with detailed working explanation, pros and cons, and then telling about how and why the model was created. So it was a pretty detailed video last time, and in this video we are gonna step up the prerequisite level a bit more, and then we are gonna start with encoder-decoder network. What is an encoder-decoder network? An encoder-decoder network is a type of neural network which is commonly used for sequence-to-sequence tasks like machine translation, text summarization, and question answering, where there will be a requirement for you to use a context. It has two main components, as the name suggests. It is encoder and decoder. Both components are typically RNNs, and in this explanation we'll use LSTM layers as the cells for encoder and decoder layers. Okay, encoder can be considered as a stack of layers, and for those stack of layers we are going to use LSTM layers. Okay, encoder and decoder network is not a neural network, it is a neural network architecture. Okay, please highlight the word architecture, because it will use any kind of layer which you'll use. So for example, you can use dense layers, you can use RNN layers, you can use even CNN layers. For example, if you have a task like let's say image captioning, then you can use CNN layers. Okay, all kind of these things can be done with the help of encoder-decoder network. Now, we already saw about LSTM that it is a type of RNN network which can handle long-range dependencies, and it will also mitigate vanishing gradient problem a bit, which was addressed as an issue of RNN. Now let's see, as usual, what, why, when, how about encoder-decoder network. Let's start with what is encoder-decoder network. An encoder-decoder network is a neural network that is designed to map an input sequence to output sequence. It consists of two main components, your encoder and your decoder. The encoder job is to process the input sequence and compress it into something known as context vector. It is a very important component, or in other words, we also call it as hidden state or thought vector, most commonly hidden state. Okay, we call it as encoder hidden state. Okay, now decoder will take this encoder hidden state or context vector, and then it will generate an output sequence. So this is how it will be like. You'll have your source, you'll compute embedding for your source. It will be provided to your recurrent neural network, whatever you have in your encoder. Now what you will do is, you have your targets. Again, you'll compute an embedding for that, and then this recurrent neural network information will be passed to this recurrent neural network information, and final output will be provided out of a fully connected layer. Okay, so this is how basically any encoder-decoder architecture works. Okay, instead of recurrent, if you want to put it as CNN and then let's say ANN, anything can be done. Okay, but like I said, in this example we are seeing it with the help of recurrent neural networks, because usually encoder-decoder networks, in any one of these components, recurrent neural networks will be used, because if you use image, people use image in encoder only when it requires tasks like image captioning. So in decoder, anyway, you need to use a recurrent neural network. All right, so in this case, we are using LSTMs for both encoder and decoder. That is fine. Why should you use encoder-decoder networks? The encoder-decoder networks are basically suited for tasks where the input and output lengths differ where order and temporal dependencies matter. I think this would be the perfect explanation about why you should use an encoder-decoder network. You see, let's take an example of translation. Okay, the input and output length will never be same. Let's say I'm translating a sequence from English to German. Okay, can you be sure that like if it is 5 words in English, it will be 5 words in German? No. And the order. So if I say like I am making a course on LLMs, will that be the same direct word being translated in German? No, the order will differ because each language has its own syntax and semantics. That's why I said, in first prerequisites video, I told you that syntax and semantics play an important role. So here is a sample of that. So the order and the temporal dependencies also matter. Okay, so that is where you will use encoder-decoder networks. So some of the tasks are machine translation, text summarization, and then speech recognition. Why you have speech recognition? The input, which is audio frames, will have different length than the output text. LSTMs are used because they can efficiently handle sequences, especially with those long-term dependencies. The gating mechanisms inside LSTM will help you to retain or forget information over a long period, which is useful for accurately translating or summarizing sequences, which we know right now. Okay, when you should use decoder networks? By the understanding of why use decoder networks, you can crack it up a bit with when you should use. When you have variable length for input and output, when the task require you to understand the context and temporal dependencies inside an input sequence, and when you want the output to be generated step by step based on a previous output, then also you can use encoder-decoder networks. Okay, so this is when you should use encoder-decoder networks. Now let's see how an encoder-decoder network work. So let's say I'm converting it from English to French. So let's say the example is they are watching, full stop, and end of sequence. End of sequence means like, my sequence is completed. When I give it to decoder, what will happen is first BOS token, which is beginning of sequence token, will be provided. That is what is done here, like the embedding. First, you'll embed your BOS token and that will be sent along with this information. Here you can see this information is passed at every state. Okay, and that is saying like something like ILS. Now what you'll do is you'll together provide BOS and ILS, and that is saying regardant, and then it is saying full stop. Okay, here itself you can see there is variable length. They are watching full stop, but it is ILS regardant full stop. Okay, so this itself shows why you should use an encoder-decoder network for translation. Now let's see how it works mathematically and like as an intuition way for encoder-decoder and all, and how you'll train that. Okay, so for an encoder, the input will be a sequence of words or tokens in English. So for example, it is I am learning deep learning. When you are processing it, each word will be embedded. Each word or token will be embedded into a vector by using vector word embeddings. Either you can use your word-to-vec, GLOW kind of pre-trained word embeddings, or if you think like those are not enough, then you can use something like a custom NN.embedding layer. That is also possible. You can use that as well. Okay, so the LSTMs here keep an internal memory. So yeah, the sequence of word embeddings again, I missed that point. The sequence of word embeddings is fed into the LSTM encoder, which processes the sequence at one step at a time. One time step at a time. Okay, one time step. So what does it mean? Like, when I provide the word embeddings, each of these are going to be considered a time step. I am learning deep learning. So what LSTM encoder will do is it will process each of these one at a time, and then it will keep an internal memory of the previous words by using its cell state and hidden state. As we all know that it has those forget, input and output gate, which will decide whether like what information it want to keep and what information it want to discard. At the last time step, the word learning, the encoder will when you process the encoder word learning, the encoder outputs a context vector which is a compressed representation of the entire input sequence. Okay, so when you process this, you will have a representation, again, that is known as context vector or hidden state. That is a representation of this whole sequence I am learning deep learning. This context vector contains the LSTM's hidden state and cell state at the final time step. So if you process the entire sequence, it means it has seen the entire sequence and now it has the knowledge of this entire sequence. Okay, so that is why the final step, what embedding you get out of the LSTMs at the last time step, it will be a compressed representation of the entire input sequence. Mathematically, how it works is, for an input sequence, you will compute the hidden state and cell state at each time step, HT, where you will provide XT with the last, previous hidden state and cell state. The final context vector will be H_T, and that will be provided to the decoder. Okay, that is how mathematically it is done. In decoder, what happens is, you will provide a start of sequence token or beginning BOS token, both are fine. While processing, the decoder will use another LSTM network that will generate the output sequence one word at a time. Now we are considering in this example that you are using word level tokenization. Okay, so that is why it is said as word. The decoder is another LSTM network that generates one output word at a time. So at each time step, what you will do is you will take the previous word embedding and the context vector, and that will be provided as input, like I said here. So if I say it is BOS, it is saying IELTS. BOS and IELTS will be provided together, and then that will say recorded. That is what they are trying to say here. Okay, it outputs a predicted word, and this word is again fed back for the decoder for the next time step. This will continue until the decoder generates a token known as EOS, which is end of sequence token. Here it means that it is end of translation. For each time step, there will be an output here, H-T and C-T. Here, Y of T-1 is the previous word. YT-1 is the previous word. Let's say if you are starting with SOS, okay? And H-T-1 and C-T-1 is the previous hidden state and cell state of the decoder. While you train the encoder-decoder network, you will train it both together. Backpropagation also will happen together by using a loss known as cost entropy loss, which we saw previously already. The model will learn to predict the correct sequence of output given the input sequence. Since we use LSTM, the backpropagation will be backpropagation through time. If you see an example, here I'm saying I'm learning deep learning. It is Jesus aprendre le aprendiz. I'm sorry for my French, but there is a sample here. Okay. In encoder, what happens is, for each of these token, there is an embedding being computed. All of these are provided one by one to the LSTM cells in the encoder, which will provide a hidden state and cell state for each word. Finally, context vector is obtained after processing all of these words, which will look something like this. Okay, and the decoder time, step by step, what happens is, first time step, SOS is provided, which will predict the word ja. And then in the next time step, you'll provide the ja along with the context vector, which is here already, and it is saying SUS, and this process will be repeated until EOS token is predicted. This is how an encoder-decoder works. So as a summary, you can say encoder-decoder is a network which is designed for sequence-based tasks where input and output lengths differ, and here we have used LSTM to maintain long-term dependencies. The encoder's work is to compress input into a context vector, and decoder's work is to generate an output sequence word by word or token by token based on the context vector. So the main thing is, this architecture is highly flexible and can be adapted to various applications like machine translation, image captioning, speech recognition, and so on and so forth. Now that we know theoretically on how an encoder-decoder network works, let's create an encoder-decoder network for translation. Here I have a Jupyter notebook. Again, we are not going to train it with that. We'll train with the script. But in encoder-decoder network, we are going to step this up a bit by adding a simple component, but which has tremendous upside to it, which is attention. We'll see about that. Okay. So first, we are going to use sequence-to-sequence model that we know. This is a model which will convert an input sequence to an output sequence of variable length and has some temporal dependencies in it. So for these, we'll use encoder-decoder. For attention, we are going to use a mechanism known as Bahdanau attention, which allows the decoder to focus on different parts of the input sequence at each time step, which will improve the model's ability to handle long sequences and complex relationships. Okay, so what does this mean? See, I have an input sequence here. I am learning deep learning. Okay, if I don't provide an attention mechanism, each word will be provided equal importance. Okay, but when you add an attention, it will process these sequences of different parts in different ways. Okay, so that is what is attention mechanism. So for example, a lot of importance will be given to words like learning and deep learning. Okay, because those are very important here. Am is not at all important. I would have been more important than am, like that. Okay, so what are these attention neural networks? Attention neural networks are neural networks which incorporate attention mechanisms to dynamically weigh the importance of different input elements while generating each output element. For example, if I want to generate an translation, right? If I want to translate output of, let's say, deep learning, I need to focus more on deep learning rather than, I am and all. Okay, so that will help you a lot. That's why we are going to add a component known as Bahdanau attention. We know about the encoder-decoder model, but here we are adding an attention to it. Okay, so let's see how the model will look like. This is how an encoder is. Like, it sounded very big, right? I'm not sure how it sounded for you. It sounded pretty big for me when I was learning it for the first time. But it is very simple. All you need is an embedding layer, and then an LSTM layer, and then a dropout. Dropout, like I said, is for regularization. So what you will do is, first you'll compute the embeddings for the tokens. You will apply dropout for regularization. You'll provide it to your LSTM and then get your output hidden and cell state. And that is all you do in encoder. If you print your encoder, let's say my input dimension is 10, embedding dimension is 512, hidden dimension is 1024, num layers is 5, and then dropout is 0.0, let's say 0.1. Okay, so if this is my encoder network configuration, this is how it will look like. Okay, so LSTM will have 5 layers. 5 layers of LSTM, it will go through all of those. Okay, so this is how my encoder will look like. So the explanation is that it uses an embedding layer to convert input tokens into dense vectors, and then it will use a multi-layer LSTM based on the number of layers we provide. And then the forward method returns the following outputs, which will contain the hidden state for each input token, which will be useful for attention computation. The final hidden state of the LSTM, which is your context vector, along with the cell state. Okay. Now, Bahdanau attention mechanism. Bahdanau attention mechanism is a key innovation that allows the decoder to focus on different parts of the input sequence at each decoding step. How will it look like? Okay, how the architecture will look like when you use an attention to it. That we are going to see now. Without Bahdanau attention, this is how it will look like. You'll provide the source to your encoder by computing the embedding. It will create all the recurrent neural network, and those state will be provided to the target. That is how it works, right? But here with Bahdanau attention, what happens is you'll get your recurrent information, and that will be provided to something known as attention. Okay, and those information are still provided to recurrent neural network. In the target side also, the attention will be the information will be added to the attention. So this attention will aggregate all those information and say, like, this is where you need to focus for your next output. So that is why there is a self connection here. Okay, this is how a Bahdanau attention mechanism works. So Bahdanau attention mechanism is nothing a lot of complication and all. It is just gonna be a linear layer, and then you'll use tan function because that will say that intensity of how much you need to focus. If you remember about the memory gate, you'll know that tan is very good for these kind of situations because it says where you need to how much you need to focus, like that, right? So the attention goes on like this. The attention layer is nothing but a linear layer here with dimension being hidden dimension cross 2 comma hidden dimension. Why? The attention will be computed on both hidden states and encoder output. Hidden state is nothing but your context vector. So along with that, you'll use your encoder outputs for your attention because hidden state is a compressed information while encoder output will have the overall information about the encoder sequence. Both are almost similar. Okay, so what happens is you will first take the hidden state and encoder output and format it in such a way that both of these are having the same shape. That is what has happened here. And what we'll do here is we'll concatenate those two together. Okay, at dimension 2. Dimension 2 is nothing but your embedding dimension. At embedding dimension, these will be concatenated together, and then you will perform an attention mechanism, after which you will call a tan function, which will say, okay, this is where you need to focus. Okay, this is how the attention is. And then what you will do is you will provide it to another linear layer, which is self.v, which has a dimension of hidden dimension comma 1. So it will say this is the token you need to process. Okay, this is the information you need to process on. That is what is hidden dimension cross 1. So now what it will do is, now you will apply a softmax function which will classify and say this is basically how you need to focus, because it is like your flattening which will happen here. And then what you will do is once you compute the softmax, it will say the probability for each token where you need to how much you need to attend on. That is what is in the explanation here. It calculates an energy score where you will first concatenate decoder hidden state with encoder output. It is a decoder's hidden state. Okay, and then what you will do is the concatenate vector. Why it is decoder hidden state? Here you can see this is being provided from here, right? It is decoder hidden state. This concatenate vector now will be passed through a linear layer, which is self.attention and the tan activation function. That is what is here. Okay, so what this another linear layer will do is that there will be another linear layer. It will reduce this to a single score. This will be across dimension, but it will reduce to a single score because you have a single sequence, right? This energy score again will be converted into probabilities using softmax, and these weights will determine on which part you need to focus on in the input sequence so that you can generate the next output word correctly. Okay, this is how the attention mechanism works. All right, now let's see about the decoder. The decoder will take an embedding, an LSTM, a final linear layer output, and then you have a dropout. Okay, so first you'll get the input, you'll compute the embeddings, and then you'll apply a dropout. And then what you will do is, right now for the first time step alone, you'll take the hidden of -1, which is ht -1, and that information is your beginning of sequence token. Okay, and then along with the beginning of sequence token, you will provide your encoder outputs, which is your context vector, together. Here you can see the self.attention is attention being provided, and that attention is nothing but a Bahdanau attention. Okay, so once you provide that, you will have your attention related information, and that information will be multiplied. That is what is BMM, batch multiplication, batch matrix multiplication with the encoder outputs. Okay, in the encoder outputs, you will multiply the attention information, and that will say this is where you need to give the importance. This token is very important because the token information is there in the encoder output, and where you need to focus on is there in the attention related information. So if you multiply both of these, you are going to get a weighted information on, say, like, this token, you need to focus this much. So that is what is obtained from here. And now this becomes your RNN input. And once you provide this, you will get an output hidden and cell state. And that will be provided to your fully connected layer, finally providing a token. Okay, so we'll also provide this hidden and cell state along with the predicted token, so that in the next time step it can be repeated, the process can be repeated. Okay, that is what is provided as an explanation here. And in see, as a whole, how the architecture works is, you will first initially have everything as zeros. Okay, as far as outputs is concerned, because you need to fill there. First you'll get the encoder outputs, and then what you'll do is you'll go through the length, max length you have, and what you'll do is you'll provide each, the output and hidden state being combined to the decoder, which will provide an output itself. And then what you will do is you'll use a method known as teacher forcing. Okay, teacher forcing is a method where what happens is, let's say your token is the task is to convert English to Tamil. Okay, and it says I love AI. Okay, and it translates in Tamil as எனக்கு AI பிடிக்கும். So when the translation happens while training, if it says I as nan is also a word to say about I in Tamil. When you are using teacher forcing, what you'll do is, instead of using nan, you'll replace it with எனக்கு. Okay, so that is what happens with teacher forcing. It is, you'll force your model to generate the correct token by providing it with information which is there in the ground truth. The information which is there in the ground truth becomes your teacher. That is what is teacher forcing. So what we are doing is, the ratio is 0.5. So whenever there is a possibility of 0.5, what you will do is you will replace the most recent token with the correct token at that time. Okay, so that is what is teacher forcing, and that mechanism is used here. So here you can see it is usually used for training stability. Okay, so how the training loop will be, we'll use the multi 30k dataset of German to English translation. We'll first build the vocabulary for both languages, and then we'll create data loaders for batching and training. A model architecture is implemented, which we already saw here. We'll define the training and evaluation loops. We'll use Adam optimizer and cross entropy loss for this. We'll also implement teacher forcing during training, and this is a strategy for training recurrent neural networks where you'll use ground truth as an input instead of model output from a prior time step as an input, so that it is more stable and learns a lot more. For evaluation, you'll use a method known as blue score, and this blue score is very famous for evaluating machine translation task, for comparing it to human translation, where what it will do is it will check for word and phrase matches. So the range at which this happens is, it is between 0 to 1, with higher being better score. Okay, this provides functions for you to translate individual sentences, and finally we'll calculate blue score on test set. Okay, so this is how the flow is, and now let's see how that happens. Okay, so here we have the training code. I'm not going to speak about the model architecture and all. Okay, I already trained it because it took some time. Okay, so I already trained it. We'll infer it though. Okay, so here you can see we have set some loggings here. Seed is set. So this is how the data set is constructed. We'll get the source file and target file, which is nothing but the txt files of German and English. And then what are all the transformations you need to do on the source sentence and target sentence, which is there here. Okay, so what we'll do here, first we have an auxiliary function known as load data, which will load the file based on the file path. Okay, so it will read lines, which means you'll have a list of data. Now this self.source data will become the length, and we'll call the data at that index, will transform it, and then will provide the output, okay, as source and target. For tokenization and all, we are going to use Spacey. So Spacey is a library which has a lot of NLP functionalities in it. One of those is pre-trained tokenizers, and we are going to use that for Spacey D for German tokenization, and Spacey EN for English tokenization, which is your target. And the vocabulary is decode news SM, which is something you need to install. Okay, so first for that, what you need to do is Python-m Spacey download decode news SM. You need to do this along with Encore web SM. Okay, here we have two helper functions, which is tokenize D and tokenize EN, where what happens here is with tokenize D, first you will normalize your token by computing it to a lowercase, and then you'll tokenize it with the tokenizer appropriate to the language. Now, here are the training parts. I've already provided all of those here with the resource folder. You'll have all of these files in your resource folder, so you need not worry. What we are doing is we are creating instances for the multi 30K data set for each data, training data, validation data, and test data. So what you need to do is just provide the file path along with the tokenization transformation path. Tokenizer. Okay, so basically what it will do is it will tokenize the sentence and provide the tokens for source and target. That is what will happen with the data set. Okay, so now we need to create the vocabulary as well. Here we have the part token, start of sequence token, end of sequence token, and UNK token. This is unknown token. Unknown token is used when there is an occurrence of a token which the model hasn't seen before. That is what is unknown token. So create vocabulary is used, and that is nothing but you'll just take set. If you call the set on the vocabulary, what it will happen is it will give the unique words. That will be a vocabulary. Okay, that can also be done better like this. Okay, so now what we are going to do is we are going to tokenize all the sentences which are there in the training data. So that is done here. Train D tokenized, train EN tokenized, and then we have computed vocabularies for that. Now you have source vocabulary, target vocabulary, tokenized training data set. Here we have defined the model architecture, which is already there. And what you need to do is you need to provide these model hyperparameters. I have set it for 256 embedding dimension, 512 hidden dimension. Hidden dimension is the dimension with which your feed-forward network works. And I've just used 2 layers. You can use more. That is your wish. And encoder-decoder dropout probabilities have kept it pretty high so that it doesn't overfit. Okay. So this is how the model is created now. Now I'm creating an optimizer of Adam by providing the model parameters. I haven't provided a learning rate. By default, I'm just leaving it to be default, and the default learning rate is 1e minus 3, okay, 0.001. And then for loss, I'm using cross entropy loss, and what we're doing is we'll ignore the padding index, and padding index is the index of pad token. Okay, so collect function is the function which will create the batch. Okay, so that is what happens in the collect function. So what here we will do is we'll replace the tokens which are to be padded. Okay, so for example, my sequence length is 512 and I have only, let's say, 200. So the next 312 sequence 12 tokens will basically be padded with the pad token. Okay, so that is what pad sequence is. Pad sequence is a function which will by default do that, and that function is from utils. Okay, so that will provide you your source and target batch which is ready for training. And in training loop, what happens is you'll set the model to training. Your epoch loss will be set at first as 0. You'll go through the source and target values in the data loader. I've just provided TQDM so that you will have logs and then you can monitor what is going on. You'll first set optimizer to 0 gradient, and then the model will be provided with the input, it will provide an output, and then what you will do is you will take your target, which is your label, you will compute loss with that, you will call the backward propagation, and that will be ready for backward propagation. Your clip grad norm is done so that it doesn't fall into exploding gradient. Okay, it doesn't fall into exploding gradient. And then what you'll do is you'll call the optimizer.step function so that the weights get updated, and then we are just adding those loss so that we can print the loss. Okay, in eval what you will do is you'll go through the values again, and then again this process will be same repeated, but the data loader would be eval data loader rather than the train. And here you won't use those optimizer or criterion because those are not required here. Okay, but still loss calculation, those are going to be the same. This is very important. This is translate sentence. Okay, translate sentence is the function which we will use to translate the sequence which is in German to English. So tokenize D, first what it will do is it will tokenize your sentence which you provide, and then it will add the start of sequence and end of sequence token. Okay, so you are getting the indices of those tokens. So what you will do is you will create the tensor. The source indices can be set as the input IDs. Okay, these input IDs are provided to the encoder, which will provide your encoder output, hidden state, and cell state. Again, as you all might know, we'll provide those to decoder along with the start of sequence token. Okay, so that is what here it is. Okay, target vocab of start of sequence token will take the start of sequence token, will compute a tensor for that, and that will provide the start of sequence token ID as target tensor to start with, and then you're providing your hidden state, cell state, and encoder output, and that will provide an output, hidden, and cell state. Now what you will do is you'll see which token is the most probable token with the help of argmax, and then that token will be appended to the target indices, and again this process will be repeated unless and until you see a token which is EOS token. Okay, so finally we'll decode those tokens by calling the indices on the vocab dictionary we created. Okay, we'll ignore the SOS token and EOS token, and then finally your tokens are provided. Okay, so I've commented the training loop here. I've created the data loader, train data loader, val data loader, and test data loader. I've commented the training loop because I just wanted to show you the inference. The training is done, but still, yeah, you can also do training by just uncommenting these. Okay, right now loading the state dict will load the weights. So I have the weights stored as bestmodel.pt, which is saved with the help of torch.save function. Okay, so you can see model.stateDict is saved as bestmodel.pt, which is already available here, and I'm loading that into the model. Now the weights are loaded, which means you're like, it is like if you've seen the Matrix movie, they'll insert a CD which will load all the information to the brain of the user. Okay, so that is how like load static basically works. Okay, and now what we are doing is we are taking 3 samples from the test data, and then we are calling the translate sentence function. Okay, let's see how the model translates. So now if you see, it will just try to load this state dict into the model, and then it will try to translate the sentence. Okay, so here you can see there is some value here, and the target is 2 young white males are outside near the bushes, young men outside near their seats, something like that. Okay, so this is not an accurate one again, but we can train it for a longer time. That is there. You can adapt the parameters. Probably that could be your exercise. Compute the blue score. I'll probably make a leaderboard. Let's say we'll take 1 week from now. Okay, and let's see who gets the best model. Okay, let's keep that as a challenge of neural hacks with Vasan challenge. Okay, so here you can see a group of men wearing hard hats, something like that. So here is men hard hats, those are there. A little girl climbing into a wooden playhouse. A little girl is into a small of a wooden playhouse. So it is trying to recognize the entities correctly, but the grammar is not that good. It will learn that if you increase the layers and hyperparameters being tuned, that will happen. Okay, so yeah guys, Now you have reached the end of the prerequisites. From next video, we'll be moving into the course, starting on with the explanation on the paper. Attention is all you need. I'll see you all in the next video. Until then, happy learning. If you have any thoughts you want to let me know, please let me know in the comment section. I'm very active in that. Please let me know your like or dislike with the help of the buttons which are provided. If you haven't hit the subscribe button, please hit the subscribe button, and yeah, share it with your friends as well. I'll see you all in the next video. Until then, happy learning.